I would like to welcome and introduce our Spring 2023 seminar series. So this year we have, I think we've adapted to the times, and also this is our third year for doing the seminar series. We started it in fall 2020, and now we have more people involved in Design++, and I'm happy to also introduce the two people who have done the majority of the organization for this now seminar series. The idea is that we want to have a nice high-quality recording, so we have some experts also recording it, so it's nicely done online for the archive as well. But I would also like to take a moment to introduce Vera and Daniela, since they will be leading the conversation and introducing our speakers in the future. So just to give a quick update to Vera. Vera is a research assistant at the Chair of Concrete Structures and Bridge Design from Professor Walter Kaufmann in De Baug. I think it's also very important to note that Vera just got accepted as a doctoral fellow from the AI Center, so this is really cool. So really quite happy for her there. And so she did her her doctoral or master's with Michael Kraus on explainable AI. And this was on the design space exploration of generative design of footbridges. So this is, I think, really important, that also integrating the next generation from master's into PhD and doctoral studies, so that's fantastic. And Daniela is an architect and a researcher. She will start as a postdoctoral researcher here with Design++ and co-lead the Immersive Design Lab at Design++ starting in April after her doctoral defense. So we're very much, there's many nice things to say about these two, but that's maybe not the point of today. The point of today is to introduce our seminar series, and we'll have 4 talks this semester. So we are trying to up the quality and limit and reduce the quantity here. And if in the future you would like to see any of the past or upcoming talks, they will all be recorded and added to our YouTube channel, if it's okay with our speaker. So this is the team who kind of puts together the speaker series. So if you have ideas for an upcoming talk, a speaker, an idea, a theme, please let us know. And we're happy to add it. So with that, I will let Vera introduce our speaker today, Professor Eleni.
Okay, thanks Danielle for the nice introduction, and welcome also from my side. Thanks for joining us for this seminar series today. And I will introduce Professor Chatzi. You can see her here, but also live in a minute. And she's an associate professor at the Chair of Structural Mechanics and Monitoring at the Department of Civil, Environmental and Geomatic Engineering at ETH Zurich. And her research interests are in the fields of structural health monitoring, structural dynamics, and intelligent data-driven assessment for engineered systems. She is the current Vice President of the European Academy of Wind Engineering and led the recently completed ERC starting grant Windmill on the topic of smart monitoring, inspection, and life cycle assessment of wind turbines. She has also been awarded with several prizes, including the Walter L. Huber Research Prize by the American Society of Civil Engineers and the EASD Junior Research Prize in the area of computational structural dynamics. So far for our amazing speaker, and today she will give us insights into her research titled Robust Monitoring for Engineered Systems Towards Augmented Twins. I hope you enjoy the talk, and the stage is yours. Thank you for joining us.
Thank you very much, Vera, for the introduction. And I also want to thank those organizing the series for having me as a first speaker. I will also apologize for my voice because I'm dealing with a bad cold, so hopefully your sound system will be tested today. Let's see. Okay, so I would like to introduce a bit on what we do in the chair of structural mechanics and monitoring at ETH Zurich, which is also, I'm also a core faculty member of the ETH AI Center, so it's great that we have Vera joining the center soon with Stelian and Walter. And what I will show here is actually touching on the use of AI and ML methods, but in in a way that is interpretable for the purpose of monitoring of engineered systems. And because I will be discussing monitoring, I would also like to explain or define the so-called concept of structural health monitoring, which is effectively a chain starting from acquisition of data, measured information from different types of engineered systems, followed by, for the purpose rather, of diagnosis of their condition, their existing condition, or prognosis of their future performance. And a way in which this can be done in an interpretable fashion and where we come in as a group is essentially the use of simulation models that can take into account the underlying principles of dynamics, as I will show, but also physics. And so we do this for assessment of engineered systems as entities, but the overarching goal is to rather be able to achieve this for the system level when we're discussing populations or fleets of systems, or you can imagine, for example, components of the structural or infrastructural network of transportation, or wind farms, which is one of the assets that we are typically dealing with, where a decision has to be taken at the collective level. Okay, so the types of systems that we deal with, I probably already gave some idea, are not your typical civil engineering structures. Actually, it's also your typical civil engineering structures, but it's anything that can be considered an engineered system and on which we can install sensors and retrieve information. So we work with the Swiss Federal Railways, for example, for the use of onboard monitoring for extracting information on railway assets. Let me see if the pointer works. Maybe not so good. I'll do it from here. And then we also have a number of activities in the domain of wind energy monitoring. I'll come to that in a bit. We are, let's say, more conventional civil structures, but also engineered systems that are actually industrial assets, bearings being one such example. Now, before I explain the use of monitoring in conjunction with models, I would like to explain, as many of you probably already know, that, or what we can do by valorizing data, meaning data on its own. And to show this, I will use an example from our activities on monitoring on wind farms, where, just to put it in perspective, a lot of information is typically available from a so-called SCADA information. They're basically information on the operation of these wind turbine systems collected at the nacelle, which is the top of these turbines, and which can give some idea about the performance of the system and the collective, of course, image of what is going on at the farm level. Now, the issue here is that you can probably understand the interaction of these systems and the way in which wind affects their operation, also using physics, but to do that, you would need quite detailed CFD, computational fluid dynamics simulations, which is not always easy to achieve, and it's not very realistic if you have to take a number of assumptions. So here we try to harness the power of data on its own to develop models of the performance of these systems. So basically how wind measured in a single point, a meteorological mast in the farm, would translate into the wind that reaches these individual turbines at a specific site that is being monitored, and how this would actually then translate into engineering quantities that are of interest for the assessment of these systems. Here you see an indicator that relates to the wake effect, basically relates to the fatigue of these turbines under different wind loads, depending on their geometry and placement in the farm. And this is great because in this case, data can infer models where physics might be hard to implement. We use a conditional variational autoencoder in this case to extract this kind of a representation. So this is one potency of monitoring and extracting information. So earlier on, I explained that this was the case for engineering assets, in, for example, bearings that are essentially elements in rotating devices. In this case, we're extracting monitor information in the form of accelerations that are extracted from these bearings. And we're trying to use experiments that run or test these identical or standardly produced systems up to failure to try and understand what are indicators that could point to their remaining useful life. In this case, we can do this because these components are identical. They are massively produced. There exist several experiments that look into their life cycle up until failure. So it means that I could use data to infer such meaningful models. I'll show you that this is not always the case. The challenge in developing such a model here, however, is that data is not always regularly extracted. So in many cases, when you monitor, you could have an issue on imputation, which means missing data, data that is extracted in irregular intervals. And so here we were trying to, and we suggested actually a model that tries to perform under these kinds of limitations, a model that admits non-equidistant data that can deal with sources of information that are not regularly retrieved and still gives an estimate of the remaining useful life of the system, which of course is always easier to achieve when nearing the actual remaining life cycle of the system. Now the problem is that in these idealized cases, I had a lot of data and I was trying to extract quantities that can be observed. But the truth, when dealing with structural systems, which is probably what you have to deal with in Design++, is that many structures are unique. And when that happens, it's not easy to develop models just purely from data that can actually give you information on the performance of the system at a level that is generalizable. And this means that data is not always enough. So to try and cope with this kind of a challenge, we'll have to take you here just to avoid the delay. When feeling that data is not enough, it means that it's time to bring an extra element in the loop, and this is where we try to use that additional knowledge that may stem from physics. So for purely data-driven representations, I already made the point that you can get to the level of detecting damage, which is the so-called task of diagnosis. But when the time comes to actually try and infer something that is additional to the assessment of the current condition of the system, so when you want to prognose its performance and how this will perform under different loads or in its future lifetime, then we need to bring in a physics connotation into our simulation and predictive modeling approach. This kind of marriage or linkage between data and simulation is what we call hybrid modeling, or you may have heard of as gray box modeling, and is essentially what we deal with in our chair, which is a sort of exploitation of the best of both worlds. We try to use these models for purposes of digital twinning, so to extract what we call virtualizations of structural systems, meaning a digital counterpart that can interact with a physical system feasibly in real time. And because we want to do this in real time for different sorts of downstream tasks, it also means that we have to have a computing capability that is very, very fast, almost as fast as your data is attained. So we can discuss an online predictive capability. So a lot of the talk that I will give next, or the examples that I will show you next, will rely in this kind of online or real-time estimation. But before I do that, I would also like to show you what I guess could be of interest to many of you, which is more of the offline concept, how you can bring together a model and engineering data, not necessarily in a real-time setting, but in a way that exploits physics and some sort of observation. And to do that, I thought it would be meaningful to show you a bit on our AeroSense project, which is a project that we have here with the Swiss National Science Foundation, with colleagues from OST and colleagues from the Center for Project-Based Learning here at ETH Zurich, and where the goal of the project is to develop a new sensing system, which is essentially a foil or a thin skin that incorporates pressure-based measurement sensors. It is wrapped around curved areas. In our case, this is done for monitoring wind turbines, so you can think of it as a sleeve that is wrapped around different sections of the wind turbine and can monitor pressure. And the reason why we developed this kind of sensing solution is because we would like to understand, first of all, what is the performance of the wind turbine blade. That is oftentimes a problematic component of wind energy systems. We would like to predict effects such as erosion, which is the slow degradation of the surface of this blade, structural deterioration that could be affecting indirectly these pressure measurements, but also eventually to possibly infer what is the wind flow around the turbine, which is something we can use for simulation at the farm level. So in this case, because the system is very young and we haven't had the chance to install it in several operating wind turbines, we have to resort to the use of a model in order to be able to understand what it could give us in terms of predictive power. And that's actually what we have done as an initiating point. We have used engineering models of these blades, which we use as emulators of the response of the system. And basically, we use them to generate artificial data that we hope is close to what the system would monitor in the field. Of course, when you use a model that is not a precise, it cannot always be a precise representation of the system, this has to be done in a probabilistic way, and that's indeed what we did. We generated series of operation of these blades under different environments, emulating on the basis of existing literature model what the erosion process would mean for the blade and how it would affect its aerodynamics and pressure. And then we used the sparse information that we get from these foils that are just wrapped around sections of the blade to show that using transformer representation, we can actually pick up meaningful readings and track the eventual deterioration of the system, which is what we would like to implement in the field. So in this case, the model was there to make up for the missing observation we have, but it's also a means for us to fuse physics into the operation or into the diagnostics of the system. A more explicit way to understand that is what we did as a next step, where we use the blade section that I showed you before, and we use this information that we get from measurements of pressure around this airfoil, and we try to extrapolate this information in order to recreate the flow around this wind turbine blade, and basically then extract this information to understand the wind flow and the mapping of the wind inside the wind farm, and also then understand how this affects the structural performance of these systems. To do this, we actually use a graph neural network representation. It's basically a representation that tries to replace a meshing, a structural mesh that you could use in CFD or structural simulations, which is here, of course, powered by the underlying use of a CFD simulator. So again, there is physics that's generating data on the basis of which a model is trained and eventually is able to give you predictions of the reconstruction of the wind flow around this airfoil in a way that very well approximates at least the baseline that we're simulating. So the idea here is to understand better what we can get with monitoring and to do this in an offline way. But of course, this once again exploits knowledge that comes from physics. However, for a great extent of tasks that have to do with monitoring, this offline kind of approach is not necessarily enough, especially for digital twinning. So when you indeed have a cyber-physical system, a system where the numerical and physical model have to operate in the loop, it's not possible to rely on offline simulations, but rather you would like to have something that is interacting or is interfacing with your system on the fly as data is attained. And so that's what we do in most of the simulations that we focus on, assuming that you have an engineered system that is operating under complex, possibly dynamics, because oftentimes the systems that we monitor are dynamical systems. This is where most of the rich information about structural performance exists on vibration and dynamics. We also have systems that operate under varying environmental and operational conditions. This is a challenge because this means that the behavior of the system has to be conditioned on external factors. Otherwise, you cannot reliably understand performance. We have to deal with systems that have distributed excitations. I spoke of wind and wind turbines, but also in buildings, you have similar effects, or you have, for example, bridges that are traversed by traffic, which is a type of excitation that is distributed but never precisely measured. And we have to now try and bring some sort of engineering model and this data in the loop in order to describe the system through its virtual twin. There are many reasons why we want to do that. At least in my group, some of these reasons have to do with hybrid testing, which is an experimental exploration of systems where part of the system is in the lab and part of the system is simulated with actuation applied onto the system through real-time numerical simulation. We have to do this for purposes of vibration mitigation and control. So in our case, we experiment with solutions of installing damping systems onto structures, typically buildings or bridges, where we try to also extract information from the response of the system in real time and feed it back into the control loop. Again, this has to be done on the fly. And we also have applications on early warning. So seismic monitoring systems are a very good representation of such a cause, where you would like to have a smart tagging and labeling of buildings and potential damage soon after an earthquake event, for example, occurs. And this is possible through monitoring, as long as the computation can be done fairly fast. So how to bring these two systems in the loop, meaning the physical counterpart, but also the sparse measurements from the actual operating system. The way in which we follow in our group is a so-called Bayesian formulation. For some of you, this might be a term that you have met in different contexts. The context that we're using it is the so-called real-time context, where you have a numerical model feeding a prediction of your system, complemented with information that come from sensors, and at the end of the day, offering a prediction that is improved because it can account for possible modeling errors, but also possible noise that could be contaminating the information that come from sensors. The principle operates roughly as shown in this diagram, where we have the engineered system. We have some sparse measurements that are extracted by means of the sensing systems we have installed. We usually, as I mentioned, have unknown. We never perfectly measure loads, so the inputs are not neither precisely known, and they can also be distributed. And we also have information that is an a priori model that we can set up on the system as engineers, but which is never perfect. And I assume you probably have come to terms with this reality, since I know that many of you deal with experimentation, and probably a prediction is never precisely describing the outcome you obtain. So there are unknown parameters, most likely in the models that we set up as engineers. And we have to deal with all of that and fuse it in a way that can offer us a prediction or an improved prediction on the output of the system. And by output, I mean a quantity of interest. A quantity of interest could be, for example, the strain in the critical location that is not being measured, the deformation of the system in its full field, and anything that is essentially a virtually sensed information, where virtual sensors basically imply the extraction of response of the system in unmeasured locations. A digital twin is really heavily relying on such a concept, because when we monitor, we really, or when we monitor a system, we typically want to know more than just the bare minimum of what we observe. And the glue to making this happen is the physics-based model. But there's a number of challenges that come into play when you're trying to conduct such an inference. The first one being the uncertainty that exists in all of the aspects of what I describe here. You know, the model is never perfect. The sensors are never noise-free. They're usually few and sparse. The fact that systems are not always behaving nicely. So if you're dealing with thin shell structures, for example, you should know that there's nonlinearity likely there. That is not very easy to model with conventional means. The observations we have are usually from low-cost systems that could be, at this point, more and more, but always are finite in number. And there's further the large dimensionality, which is really the curse of real structures. They're not very nicely behaving simplified systems, but they're more complex, and they are described by a large number of degrees of freedom. So in our group, we deal with structural mechanics. This is actually a topic we teach. And traditionally, structural mechanics has always been concerned with how to simulate actual structures, so multi-degree of freedom systems, in a way that is computationally efficient. In the slide, I'm accumulating some of the typical approaches to doing this, and there exist ways to accelerate simulation with easy, let's say, not tricks, but ways to reduce the modeling of the system into something that computes faster. We can do this for fracture. We use extended finite element methods to simulate the systems that are cracked and do it in a cost-efficient way. We can do it for nonlinearity or material plasticity. Again, there are multi-scale formulations that allow you to compute something that is a nonlinear structure in a faster way. We can do it with substructuring when we're dealing with systems that are sub-assemblies or are comprising assemblies of multiple components, like wind turbines is one of these, for example. And we can also compute faster for systems that experience geometric nonlinearity, like those thin shell structures. But a lot of these ways, although they can be computationally faster, they're never fast enough to allow us computation in fragments of seconds, which is how fast our data is accumulated. So we need to do better than that. And one way to boost this kind of a computation is to use a machine learning type of approach where you try to develop a surrogate of what we would call full order finite element model by representing or replacing this full order finite element model with an alternative that computes faster. Such an alternative can be given by an autoencoder setup, or specifically a variational autoencoder setup, and I will explain later why, which can admit simulations of the response of such an expensive system, boil them down into few representative parameters, even if the system is actually nonlinear in behavior, which is typically more complex than a linear structure. And because we have to simulate dynamics, it turns out that you can actually link this reduced latent state or latent state space with recurrent neural networks. In this case, we use an LSTM to do that, where we can link the force that comes into the system at each fraction of time that we have data for instance, solve our equations in this reduced space, which is non-physical, but we don't actually care, because once we understand what is the response of the system in this reduced space in the next point in time, we can use the decoder architecture to go back into our physical space. And this for us is very important, because in monitoring, we monitor actual physical coordinates. So it would not mean much for us to simply just stay into this reduced dynamics. But in fact, we can recover any quantity of interest that we're interested in from a finite element model by using this decoder architecture. We have validated this approach first on a benchmark that we have set up for the structural engineering community. This is actually offered in the platform for the nonlinear benchmark workshop. This is a nonlinear plastic system. It's a shear frame, which where every node in this frame is a hysteretic link. A hysteretic link basically means a connection that just has this kind of hysteretic nonlinear behavior. And this is a multi-degree of freedom system. So we wanted to see if we could reduce its response under different types of earthquakes and compute in real time. And indeed, it turns out that you can do something like this for such a nonlinear system. You can even do it by conditioning on the characteristics of the input load, like the earthquake, because earthquakes as well can be parametrized as loads. And the computation in this case is indeed something that is enough for us, or fast enough for us to use together with the data as this would be assembled, assuming the system is monitored. I don't want to stay too long in this slide. I just want to say that we have validated this actually also for in experimental data from such a shear frame with nonlinear mechanisms. For those interested, I will say that the variational autoencoder makes a difference, because it extracts a latent state that has orthogonal components, not orthogonal, but independent components, which means you're trying to approximate what we call in structural engineering nonlinear normal modes, which is particularly important for nonlinear systems. And then we have also verified it with our collaborators in Denmark with Siemens Gamesa, who have offered us a set of simulations, nonlinear simulations on the soil structure interaction of such wind turbines that are based on soil. The behavior of soil is nonlinear, and so we have used this concept to give them a surrogate that computes dynamic response given these nonlinear springs, but replaces the actual finite element simulation, and does so, again, by computing at a very accelerated rate. In what I showed, I briefly mentioned that you could also condition on parameters, but I would like to explain again for those interested that when you want to do such reductions, and you want to do it for systems that are parameterized, meaning that they operate under different conditions, or you want to explore their behavior for different material parameters, the more formal way to do such a reduction would be to use what is called the parametric or parametric reduction, or a projection-based reduction approach. In this case, again, we're concerned with the dynamics. For those who have a structural engineering background, dynamics is actually typically represented by such an equation. And what we would like to do is replace this expensive simulation that's usually done with finite elements, again, with something that computes faster, but is this time conditioned on a set of parameters like material or geometric parameters, or parameters of the loading that is acting on the system. We do this using a Galerkin-based projection approach. And I don't want to go into the theory of this, but I would like to explain that it's something that can be easily extracted from numerical simulations again. So you use your model, or full order model, as an emulator. You generate the response of the system under different sets of parameters. And when you do that, essentially a singular value decomposition on those response time histories would then give you these matrices that are basis matrices that can take us from an n-dimensional space, which is quite large, into an r-dimensional state. So a representation that's very compact, and it gets, again, much easier to solve. And this representation is conditioned on our parametric space. These funny figures are basically representing manifolds, so the space of parameters and the space of the solutions that we get for these different sets of parameters. There's a number of approaches to achieve this kind of parametric representation in a fast way. And we have developed a number of schemes to make this easier, but I won't, again, mention too much on the detail of this, because I would like to now bring you to this linkage between the model, which we have shown that we can reduce, and the observations. So assuming we have an equation that describes the dynamics, or a model that describes the dynamics and is a reduced order model, and assuming we have an equation that is reflecting our measurements, we can now bring the two together using the Bayesian logic that I mentioned before. And the Bayesian logic is basically a two-step procedure. It's a procedure where we have a first step of prediction, and this prediction step is what the model tells us. We use the model to predict where we are at the next point in time. And a step that has to do with the so-called update, which is essentially the step that corrects for the discrepancy between what we can predict and what we in fact measure in reality. This corrective term can then take us into a posterior estimation, a posterior estimate that is improved with respect to our original one. And again, this is a bit of a detail, so I will take you directly to the application. Here I'm showing you an application from one of our projects called SIMAERO, where the purpose was to develop reduced order models for damage detection on aerospace components. A part of aerospace components are the fuselage systems that are basically, again, thin shell structures, and where we assume we have a limited amount of sensors, the ones that I denote in red in this case. And we would like to, on the basis of these sensors, understand where a flaw, for example, a crack, can exist on this system, but also to infer what the response of the system is in unmeasured locations that could be critical. So this is a virtual sensing task, and we would like to do it in real time. So we do use the logic that I showed earlier. We develop a reduced order model that's conditioned on the parameters of the problem. In this case, for damage detection, the parameters of the problem are the location, orientation of the crack, possibly characteristics of the load that is exerted on the system. And so what we do is we take this curved surface. We generate a number of different flows that we use to generate simulations from. we encode these flows, which are basically these cracks, by using a mesh morphing approach. It's a bit more detailed, and I leave it there for those that have an interest on structural simulation, but can come to it maybe later if you have questions. But the important thing for us is that we can have a model that computes actually faster than the video that I'm showing here, and which can give us the response of the system, again, as fast as data comes in. And now that we have this, we can actually combine the data, the so-called observations, the measurements from that fuselage panel that are usually in the form of accelerations or dynamic strains. We run a series of models in the loop together with this data just because they're fast enough to compute. And on the basis of a model selection process, we can actually infer what the likely parameters for the crack positioning or multiple crack positions are, which is something that you see here as the convergence. This convergence is done as we acquire data, so as the system is actually operating. But also, quite importantly for us, we can extract the response of the system in locations that we don't measure with quite high fidelity, of course with some level of uncertainty. And we can do it at a significantly faster computation than even the most improved or highly developed full order structural models would give. So in this case, the speed up is 177 times with respect to a finite element approach. Now, in what I showed, and that's probably what I would soon like to close with, I assumed we have a model, I assumed we have data, and we're trying to optimally combine them. But I didn't say much about the case where the model could be significantly off. And again, for many of you and anyone who uses real observations and actual experiments, you might have seen that we can never have a model that is good enough to really approximate what we observe. And that's the case for many systems, at least many of the systems that we deal with, that have to do with monitoring, either using remote or attached means. They have to do with seismic evaluation of structures. They have to do with dynamics of systems that are highly flexible or highly deformable. So because our models are never precise enough, we have to find a way to compensate for them, but a way that does not necessitate the pure use of data or the blind use of black box machine learning methods. Because at the end of the day, we're still engineers. We have an idea on how our systems operate, and we would like to take that into account. In our case, the motivation for developing something like this came from our work in Singapore in the Future Resilient Systems program. There, we're developing an onboard monitoring platform where we attach sensors on vehicles, similarly to what we do with the federal railways. But in that case, we want to have a low-cost platform, something that we have developed, and it's easy actually to, at this point, to try and produce at relatively low effort. And we would like to take the measured data that come from such traversing vehicles and use it for assessing the underlying infrastructure. We want to do that because by using mobile sensors, you can actually assess large pieces of infrastructure, kilometers of roads or rails, with a single diagnostic vehicle or even your common cars and common operational trains. So when doing that, we realize we can never have a perfect model of a system that is probably quite complex. But we do have a basic idea of how vehicles generally operate. Even the developers of vehicles have some models that can be used as simplified approximations. And so we use the logic that I mentioned before. We take our engineering model, feasibly we reduce it, but we admit that it is partially only correct. So in parallel, we also run a learning-based model, a model that is taken on by neural networks. For others, other researchers in the field, this is done with Gaussian processes. And we try to superimpose the two and marry them using the Bayesian logic that I showed you before, but now for neural networks, marry the observed data with this concatenation of a known and a learned model. The fusion of the two allows us to get a best fitting approximation that still understands some physics, but also accounts for the fact that we do not know all of it. So here's what it looks like for our onboard monitoring problem. What we basically did is we tampered with the architecture of the so-called deep Markov model. The deep Markov model is a Bayesian filter, is one of the, which basically follows the logic that I showed before, a step of prediction and a step of updating. So here is the updating based on the sensor data. Here is the prediction based on a neural network concatenated with a physics-based term. All of them operate with some assumption on probabilistic uncertainty underlying these predictions. And when you combine the two together, it turns out that you can estimate quantities such as, for example, the roughness of a pavement. Pavement is the surface of the road. When you get acceleration measurements from a vehicle, I show you here how the mixing works by forcing the weighting term between the two models. This is not something we do. Actually, this is inferred. But I want to show how the behavior would operate. In the case where you rely more on the physics, you would get a slow convergence in this case. When you rely more equally on data and physics, you get something that's really not meaningful. But there's an optimal coefficient that gets you into a very good prediction at a short amount of time. We're actually using this logic with sensors mounted on a smart vehicle. Access is offered to us by the MIT collaborators we have on the campus in Singapore. And we're trying to use it for assessment of roads, but also exploit this logic for further applications. I will try to skip this example and take you here to show you that this idea of including physics is highly beneficial, and we have been exploring it beyond the previous application that I showed you, which was on the physics-guided deep Markov model. We also work on so-called neural extended Kalman filters. Again, it's a way to bring in structure and some idea on the physics of the quantity that you observe into the simulation. And the symplectic encoders, which are basically Hamiltonian neural networks. It's a way to include physics constraint into the prediction of dynamical systems that are actually physical. The reason for doing this, as always for us in monitoring, is to be able to understand how a system performs and feasibly understand if there is damage that is inflicting the system. We have validated this on an experimental application using a blade that we have tested here in the IBECA lab. We have tested this blade under damage scenarios. We have generated different flaws that are characteristic and occur on these systems. We have attached a network of sensors, and we would like to understand if we can simulate the system and then understand if damage occurs under different humidity and under different environmental conditions. That's why we tested it in a climatic chamber. And indeed, we did this. We used the logic that I showed you previously, and we trained our model under so-called baseline or healthy conditions. In this case, we have a very good prediction of the dynamics of the system after the first training. But of course, when we go into the other cases where damage comes or different environments are acting, we start deviating. And we're using this sort of discrepancy between what we predict and what we measure to classify the damage and even try to characterize it for different levels of intensity, which is one of the primary tasks of SHM or monitoring, to detect, quantify, and physically localize damage. And then I want to close with, after following the logic of the chain that I showed you in the beginning, what would come next and how would we be able to go to the last stage, which was decision support at the system level. To do this, we're exploiting a logic that capitalizes on the indicators, condition indicators that we extract from monitoring, and which tries to map these condition indicators into spaces of decision on what action to take on a system, such as, for example, for a bridge, what would be, in case of a specific indication of the condition of the system, what would be the best action to take to repair components that are faulty. For example, for a bridge system, in this case, we were experimenting with cases of joints where you're wondering whether to weld a defective joint to possibly paint over a corroded part of the system or completely repair it. Each one of these actions comes with a different cost and a different effect on the condition of the system after it has been repaired or interfered with. And additionally, another decision to take is what kind of inspection should I then take onto this system to understand where my condition is. So in order to navigate through the space of these decisions that usually infrastructure owners have to take, we use a sequential decision-making logic. This is powered by a partially observable Markov decision process framework, which again builds on the logic that I showed before. Somehow we end up following this Bayesian logic all through the chain that I showed in the beginning. And so you are advised on what action to take, what observation to then take on your system. You then, or you or the operator of a bridge, for example, can then figure out where the system is at the next point in time. And then this circle of decision, inspection, and action continues until for the full horizon of a life of a bridge. Of course, this was a simulated example, but it turns out it also works on real systems. So we, as I mentioned in the beginning, we have a collaboration with the Swiss Federal Railways. In this case, it was not a bridge, but a railway infrastructure we were interested in. We use our onboard monitoring data to extract an indicator of the condition of the subsoil, which is basically the soil or the underneath the rails and tracks. And so we use accelerations to extract the so-called fractal value indicator that gives us an idea on what is the condition of the system, whether there is actually fault that comes from moisture presence, whether there is a distortion of geometry. And depending on the values of this fractal indicator, we can use this sequential decision-making logic. So what is the condition we suspect? What is the inspection information we have? Or what is the monitoring information we have? And advise the Federal Railways on what is the best action to take when a fault is detected so that we can minimize the costs and optimize the repairs for the horizon within which they have to manage this asset. We do something similar also in Munich. This is part of a fellowship, and this is the work of Antonis Kamariotis, where this sequential planning of decision and actions with concurrent information on monitoring is placed within the framework of value of information, which essentially means that we, at any point in time, we try to offer operators not only with the best possible decision, but also for a margin of uncertainty on what this decision could mean about the future handling of their infrastructure in the face of extreme events, but also under prolonged deterioration effects. At the end of the day, what we would like to have is what the title of the talk was hinting at, which is essentially this concept of an augmented twin, where you have a physics-based model, possibly reduced, running with data that you extract from the field, complemented with information that comes from experts and from their tendency to take and assume decisions, and transfer this to actual scale systems that tend to not be individual structures, but rather fleets or populations of structures. So with this and the featured members of the group whose work you saw in the slides, I will conclude, and I'm happy to take any questions. Thank you very much.
Thank you very much for your nice presentation. Maybe I can ask the audience first if you have any questions on this nice presentation. No? Then I might go ahead. In the beginning, you had proposed that you want to take both worlds, the data world and the physics-based world, and combine them with each other. And there was also one bullet point there labeled explainability and interpretability. And I was wondering if you could maybe explain a little bit more what you have in mind for tackling that.
This is actually the primary driver as to why we're doing this, the fusion of physics in the loop, is because, and again, this probably relates more for those who have attempted to model structural or other systems using purely neural networks, for example. you can observe that the inference of the model, which is the neural network, does not necessarily have a physics-based connotation. So while we can reproduce the quantities of interest and basically what the neural network is trained to give as an output, we cannot say much more about the rest of the system, which is not being monitored or whose, for the properties that have not been used in the training. And in monitoring, this is a bottleneck because we cannot observe everything and we would like to know more. So to do this, to get explainable models, we have to find a way to fuse physics in some form, either wholly, if you have a good approximative model, or partially, as I showed in the case where you try to concatenate a learned model from neural networks and a model that partially reflects what you know. The benefit of fusing even this partial physics-based information is that you recover a fitted function whose states are actually closer to physical states. And you get information that is more than the information you probably observe that still have a physics-based connotation. So they are explainable. And that's why at the end of the day, for us it's important because then we can show it to the operators and the engineers who have to decide, and it's not a black box function. It's probably a displacement or a strain or something they care about that we presented.
Thank you very much for elaborating. Yeah. And maybe also there is also a person here wearing virtual reality glasses. So maybe to break it down a little bit in more simple terms, how would you imagine to show this to a person that doesn't know how to?
This is a good point. I'm using this graphic. It's actually a graphic that we have submitted for a proposal because this is something we're working on with colleagues and we would like to see it soon materializing. The idea would be to take exactly the framework that I showed and indeed bring it in what we call a virtualization to the engineers, to the operators, again, the decision makers. In my opinion, the most prominent way to do this is to offer a visualization that is interpretable for them. And you likely know, and I think it's part of the Design++ even, to use this kind of technologies, that you could use augmented reality to deliver the simulation that we're predicting, for example, through our fused models, and overlay it over a physical system, or just give it to the engineer to imagine it, but actually to visualize the prediction of the quantities that we offer, not as time series data, but an actual deflection of a blade. This is something we do actually with Siemens. They already have produced such a virtual reality platform that can give you the deflection of a blade under different wind loads, allowing the engineers to consider what the design means in that case, or if it's an operating system, to understand whether it's actually being fatigued or if it's being loaded more or beyond the expected performance. And I think that's really something we will be certainly doing in the future. It's probably a better way. It gives us a way to have a vocabulary, a language that is understood by practitioners and that just doesn't just stay in academic plots and figures. So I think it's quite important.
Thank you very much for your elaboration. Are there now any more questions from the audience? Yes?
Thanks for the presentation. And I was wondering, so the models that you, why I'm so loud? The models that that you have from one structure, for example, how if you assess or if you take measurement in one bridge, how does it actually extend to another one and that typology?
But you're right. This is one of our biggest concerns, how to do transfer between systems that are similar or even systems that are not necessarily similar. For example, in a paper with collaborators from the University of Sheffield on what we call population-based SHM, the idea is to show how, for example, damage detection performed on an airplane blade could relate to damage detection on a frame structure, on a building structure, for example. The systems are dissimilar, but the traits of the dynamics and how these change between interconnected degrees of freedom actually proves to be more similar than we expected. So there is the possibility of transfer, and a very good way to achieve such transferable and generalizable models in my opinion, is to use graph-based representations. So for example, when you reimagine a structural mass as a graph neural network whose attributes reflect the stiffness and whose nodes reflect the interconnection of structural elements, then by redefining these attributes and even the geometry, and we have such a case for simulation of wind turbines, for example, you can reimagine these grids, which give you either a new structure or in our case, a new wind farm layout, and you can adapt that model that was previously trained for another configuration to work and to still perform on a much, either a different geometry or even a new structure altogether. This is imaginable, but in order for this to be done, you have to have a representation that really reflects the aspects of those systems that are common and allows you to parameterize with respect to those aspects that, of course, are changing. And there's limits to this, but yeah, to go to go into the details of this, one would have to start talking about observability of these systems based on what you observe with your sensors, how you model them, and so forth. But it is doable. It's very exciting. It's an exciting direction.
Okay, thank you for your question as well, Danielle.
Thank you very much, also from my side. And a question which I had is the same approach or a similar approach transferable also to design?
Yes. Design is the case that would be for us what we call the open loop case. You don't have data from the operating system, but many of the aspects that I showed in the beginning were using a full order model as the system that generates data. So in that case, in design, we usually want to be able to produce these fast representations that are parameterizable and that can replace very expensive computations, because maybe usually for structural systems, a proper design could mean the use of a finite element model that could take hours to render, to run, and to do this over different geometries, different properties of the model, could be computationally unaffordable to the point where it's limiting the simulations that you can achieve and the type of design conclusions that you can reach. So the aspect of reduction by training on data that come from simulations is definitely something that we are also using and that can be used to get these accelerated or reduced order representations that are parameterized and can be reconfigured to run for different material properties, different load properties, so you can, in a way, adapt to new domains. You could even transfer to geometries that are different. Again, using this concept of graph neural networks, you can imagine having a specific type of design for a roof by reconfiguring the positioning of the nodes in that network, but having somehow already trained for different constellations of these configurations, you can probably generate designs that have not been included in your training. All of this logic is underlying in what I showed you here. The difference is that our primary purpose in monitoring is, at the end of the day, to also combine it with data that we can extract. And I think that also for design, this is probably, is in a sense meaningful, because also here, and I think the architectural department here probably takes pride on this, a lot of the design is complemented with experimentation. And experimentation is another form of monitoring. It's not monitoring an operating system in the field, but it's actually tracking the response of a prototype that is experimentally tested. And so again there, for example, you could have an underlying model of the system, you can test it in the lab, and you can figure out what it is you're missing by using the logic that I showed you before on modeling discrepancy, for example. So there's room for these ideas all through, in my opinion, from the design to the operation, even to the decommissioning of these systems.
Okay, I hope that answered your question. Otherwise, we can discuss later, or maybe write an email if you have more extended questions.
Actually, usually I have here, but now I failed to do so, I understand. But you can find my email most likely by just looking up our chair, and we would be happy to receive any questions, and I would follow up with more details and more sources in that case.
Yes, so So from our side, again, thank you very much. We have a little something for you.
Thank you.
Thanks for coming here and presenting your work. And now I would say some final words to the continuation of these series before I let you off into the apéro. Okay, so the next talk that we will have is Professor Salter. He is from the Zurich University of the Arts. So this will be probably a completely different perspective on how computational design can be tackled. And his title will be Becoming Aware, Body Sensing, and the Transformation of Environments. If you have time, please also join then. And we're looking forward to seeing you again on the 28th of March. And now feel free to have the apéro at the back of the room. Thanks.